So this talk is about automatism. It's a mostly ignored subject for physics students, and the book I'm going by is this one, Essay on Automatism, and it picks up the idea of automatism from Democritus, who's a Greek philosopher, but some people think the idea goes back further than him, and automatism is basically the idea that physical reality or stroke the universe is made from particles. So this is the person who wrote the book. It's Lancelot Law White, and he had been dealing with investigations of unified field theory and so forth. So White says this: the conception of automatism has been the spearhead of the advance of science. Atomic ideas have led to the highest adaptive precision which the human brain has yet achieved. The history of automatism should therefore be of interest to all concerned with the human mind. Whatever the limitations and dangers of automatism, its achievements are unique and worthy of study. So automatism was originally the idea everything was made from atoms, but that term atoms got used for chemical elements. So the smallest unit of a chemical element is supposed to be an atom, and really the idea of automatism extends to physical reality being made of lots of different particles, not just chemical atoms. And White continues: until a few years ago, I imagined that courses in physics included an outline of history of automatism. Unfortunately, that is not so. Many universities, teachers and students consider they have no time for that. And this is White writing in 1961, and things haven't changed as far as I'm aware. Physics students are not taught about many important things in physics that was dealt with in the earlier 19th century. And automatism is one of those things which physics students are not usually taught about. White says there have been only three basically distinct and widely successful conceptions, and that's of automatism. They present striking contrast, and the first one is labelling as A, the Democritan Newtonian hard atoms. Is Newton's following the Greek automatists adopted as most appropriate the view that the ultimate constants of matter are themselves minute, hard, permanent, indivisible bits of matter of definite sizes and shapes. They occupy parts of space and move through the empty spaces between them. Occupied and empty space are sharply distinguished. Many scientists still think like this. So carrying on with option B, type of automatism, which White is talking about, is called Boskivian point centers. Boskiewicz proposed a substitute having several advantages. The smallest units are not extended pieces of matter, but persisting physical points evidenced as centers of interaction. Only the spatial relations of these physical points enter physics, and every pair of such points are in interaction. And type C, which is labelled type C, is the de Broglie Schrödinger wave particles. That was introduced a third, more powerful conception of automatism, that in certain circumstances the ultimate particles possess wave as well as particle properties. This idea, though substantially modified in statistical quantum mechanics, is the most comprehensive of the three and provides the basis of current atomic physics. The wave theory light had long presented a challenging contrast to atomism. Here the waves seem to have beaten the particles. Light continues and he talks about the type A is familiar but mathematically awkward, involving discontinuity at the surface of the atoms or particles. It is also inescapably associated with the idea that matter cannot act where it is not. Even Newton believed that all genuine physical action was by material contact, though he saw no way of using this to account for the law of gravitation. While type B is ideal for many purposes and mathematically convenient, it implies that each point atom or point particle pervades space, acting everywhere except where it is itself. A valuable emphasis is thus placed on interactions or changes of relative velocity, but this idea has proved too restrictive, at least as Bosquet presented it. And I'm pointing out this word here, point atom, he's talking about. As I said, the atom is usually now reserved for being the smallest part of a chemical element. So really we're talking about particles, so really should be saying point particles and not point atoms. What is labelled as type C idea is the most successful so far, but it lacks both visual immediacy and mathematical simplicity. Moreover, recent mathematical modifications have made its physical basis obscure, and I want to remind you he's writing in 1961, so things might have moved on a bit since then, and it's led to many different interpretations being offered, of course. Right, now Mike carries on and he says, to these three primary ideas must be added various special conceptions of less value, vortex rings and other rotating units, twists in a rotationally elastic jelly, dislocations or holes in a close packing of spheres, negative atoms of various kinds, and so on. And by negative atoms he's probably still meaning negative particles. There is also Eddington's ghost particle, from which he excluded all vestiges of materiality, so that it became merely a carrier of variance, or a conceptual unity whose probability function is specified by certain wave vectors. Finally, recent work has suggested that what marks a fundamental particle is not its physical indivisibility, but the possession of a definite set of fixed parameters. And I'm reminding you again, when it's using the word atom, it's probably better to use the word particle. So White goes into more detail about option C, which he refers to as wave particles. He refers to it as a disruption of the classical particle idea by the quantum particle idea. And so White says, however, this disruption of the classical particle is not solely the responsibility of recent quantum theory and experiment. And this is, remind you again, it's 1961, he's writing, for difficulty had arisen earlier in relativity theory. Einstein's aim was a comprehensive relativistic theory, and he knew that classical particles were alien bodies which should be represented if possible as unique regions in a relativistic energy field. but it was unlikely that such virtual particles or field foci could be permanent. Indeed, it seems that any time after, say, 1910 or 1915, when it became clear that negatively and positively charged particles had definite radii associated with them, Einstein might have predicted the existence of unstable particles by using the following syllogism. So this is what White says. Point 1, the laws express in terms of intervals the properties of relativistic space-time fields. Point 2, experiments have shown that some electrical particles have an effective finite radius. Point 3, therefore some electrical particles must have an effective finite lifetime. And or in dimensional terms, since L subscript O enters electrical particle theory, where L subscript O is a distance or length, and it says the formula T subscript O equals L subscript O divided by C, and T is subscript O is sort of a time, and C is of course the speed of light. And he says must enter relativistic particle theory as life period, since the interpretation of T subscript O as the reciprocal of a frequency was not possible in this context. Behind the line of reasoning lies the assumption that particles are quasi-localized, semi-permanent forms of relativistic field energy, their radii, lives and masses being properties of temporary energy distributions, which for undiscovered reasons are centered at points and which appear therefore as unstable particles. There is much evidence for this basically anti-atomitist view, in which there are no truly discrete entities but only a continuum of transformations. The power of the energy concept of relativistic methods and the discovery of many unstable particles all speak in its favour. And as White points out, that sort of leads to problems, snags. And so we have, for example, continuity, where velocity is a continuous variable, and then on the other side we have things that are discrete variables, well actually discrete values, such as E electron charge and H Planck's constant. They're discrete values. White refers to this as classical atomism has certainly encountered insuperable difficulties, and radical modifications have already been necessary. So that these problems have caused reassessment of the atomitist ideas. White says most philosophers and scientists agreed that to account for what is observed, it's necessary to infer entities which are not observed. So these particles are not directly observed. An unseen universe is necessary to explain the seen. The particles are the unseen universe. The flux is seen, but to account for its structure, we infer particles of various kinds to serve as the vertices of the changing patterns of light and shade, of colour, bright and dark, of radiant energy. Some readers of the essay will probably live to see a new picture of this unseen world. They are to be envied. And so he's writing in 1961, and he thinks things will be sorted out eventually. And sort of, he's 1961 writing, and we're more than 6 years on from that, and it's still rather complicated, so things haven't been solved. From considerations about particles, it leads to White pointing out what are the other things associated with that. You start thinking about space, metrical geometry, coordinates, time, reversibility, irreversibility, inertia, mass and force and so forth. So you have in all these ideas that are added to the basic idea of atomism of having particles. That's why it says we shall begin with broad perspectives. Physical atomism can be said to have started with Epicurus and Democritus. And as I've said, I think earlier, the idea of atomism might go back further than these ancient Greek philosophers. Anyway, and after transformations have many transformations to have reached a crisis as it is seen to us now after 1930. So you've got this basic ancient Greek idea of atomism, and in 1930 it led to a crisis, and in my view the crisis is still there. We're still having problems with the basic idea of atomism in modern physics. It might continues. This span of 2,400 years may be viewed as the life history of an idea which is born, matures, achieves its task, perhaps then marries another idea and leaves its progeny to carry on. The analogy has some value. Certainly in the case of atomism, there are moments of conception and periods of quiet growth, of play, spontaneous qualitative speculation, of work, deliberate applications to quantitative tasks, and of fusion with other ideas. So this is the life history of the idea of atomism, and in his view the idea is conceived in about BC 450 to 420, and then in a bit later on 420 to 280 BC it was a welcomed idea, and then from 280 BC to 1400 AD the idea slept with occasional play, and so not much was done within that sort of over 1,000-year period. And then in 1400 AD to 1600 AD there was more vigorous play with the idea of atomism, and then in 1600 AD to 1800 AD the idea was put to work quantitatively. Then from 1800 to 1900 AD the idea of the chemical atom came about, and as I've pointed out before, the chemical atom is only the smallest particle of a chemical element, and you can actually think of other particles. So atomism really deals with more particles than just the chemical element's atom. And then 1900 to 1930 the idea of the chemical atom was recognised to be misnamed. It wasn't the smallest unit of matter. And then from 1930 onwards the issue got confused. It's still trying to make sense of it. So this is the geography of atomism. His view, he starts in Greece about 600 BC or to 400 BC, and then it goes to Italy, where the Romans honoured the Greek ideas. Then India did pick up on the idea, and then further on the Mediterranean sort of came about the idea after the decline of Rome. Arab and Jewish thinkers maintained the memory of the Greek ideas and developed some variants. Then sort of it went to Europe. Some Christian scholars showed interest, And then in 1400 AD, Italy had a revival of speculative interest. Italy and Spain served as channels for the European rediscovery of Greek science, and I think that period is sort of called the Renaissance. Well, the start of the Renaissance. In 1600 AD, Western Europe, such as Italy, Britain and France, sort of looked at the idea. 1900 AD, it was in the Western Hemisphere, and there was experimental activity involved on the idea of automatism. So, according to White, these are sort of the main people involved with automatism, where you can think in that terms. Actually, there's a lot of people involved with thinking about automatism, and Newton did think about automatism, and then there was Boskowitz, and then there was Dalton, and then there was Prout, and then there was de Broglie and Schrödinger. And since the book was written in 1961, there's been other people since then. So basically the conclusions are the complicated issue of automatism and how it's evolved to what is now in the mainstream physics. This is early 20th century, as part of relativity and quantum physics is ignored, stroke omitted from what is taught to physics students. So it's no wonder that modern physics is messed up. People are just not being taught the basics of modern physics, which is coming from this ancient Greek idea of automatism. And I'll put that in the proviso. The idea might go back further than the ancient Greeks. Finished at the end. Thank you. I hope you enjoyed this little talk about automatism. There's lots of things that modern physics students are being not taught about, and automatism is one of the big ones. They're not taught about this idea of particles, of all the different ideas that have gone into the idea of particles from ancient times to modern times. Thank you.